Hello, everybody. This is the project review video for the GE Non-Optical Flame Detection Algorithm project for Senior Design, Spring 2023. We are Team 2. My name is Jared Copperwheat, and my team members are Reese Taylor, Bradley Riley, Wyatt Cooper, and Wyatt O'Quinn. As an introduction, GE Gas Power manufactures and sells gas turbines for use in power plants. These turbines are very large and very expensive to run and maintain. So naturally, they are constantly being monitored by a plethora of sensors to detect issues, prevent lengthy breakdowns, and enforce safe operation. One critical metric that is being monitored on the turbine is flame state. That is, whether or not flame is present in the combustion canisters. Here below, we see a picture of one of GE's 7HA gas turbines. Labeled on the image are some of the key metrics that are considered in the non-optical flame detection algorithm. So GE has been experiencing problems with flame state detection. Previously, flame state was detected using an optical sensor that was mounted directly to the combustion canisters. However, high operating temperatures of the turbine required water cooling to keep the optical sensors within their own operating range. This water cooling system was prone to breakdowns and leaks, which not only take time to fix, but also pose a greater danger to the turbine. Cool water leaking onto hot metal can cause warping. And because the tolerances inside these turbines are so slim, any sort of warping can cause many greater issues inside the turbine. So GE developed, as a solution, the non-optical flame detection algorithm. Essentially, they've opted to remove the optical sensors entirely and instead use an algorithm which monitors other sensors on the turbine to detect when flame state is out based on these other sensors' readings. To develop the NOFD algorithm, GE created a Simulink model of the algorithm and recorded data from real operating turbines to use as input to the Simulink model. One problem GE faced while developing the NOFD algorithm was that it's hard to do advanced analysis on the performance of the algorithm when the results of the algorithm are binary. Essentially, did the algorithm detect flame state correctly or not? To solve this problem, they created something called the margin score. It's a single metric calculated for each case, which essentially represents how confident the algorithm is in the flame state that it detected for that case. Using this margin score, not only can we see whether or not the algorithm predicted flame state correctly, but we can also see how close the algorithm was to detecting the flame state or not. Higher margin scores correlate to a more robust detection of state. And so using margin scores, we are able to analyze the algorithm further than just correct or incorrect detection. So the overall goal is to create a more robust algorithm. And in order to do that, we must obtain increased margin scores. And the way we increase margin scores is by optimizing the algorithm's parameters. GE's optimization efforts up until this point have resulted in a highly accurate algorithm. However, it is still not as robust as they would like. And so the problem is, in order to optimize the parameters even further than they've been able to so far, they would like to use a computational optimization algorithm on the Simulink model. However, this sort of optimization problem is a very compute-heavy task. It requires running the code over and over again on tens of thousands of cases, adjusting the algorithm parameters and checking the margin scores along the way. And with the code currently taking roughly 2 seconds to run a single case, this is just not feasible. So our objective as a team was to speed up compute times so that computational optimization is feasible for this body of code, and then to consider how optimization might be applied. Our approach to this problem came in 3 steps over the semester. First, we built a high-performance desktop computer so that we could efficiently test the MATLAB code in Simulink model. We made sure this computer had very high level core count, 16 cores to be exact, so that when running in parallel, we could get the best compute time results as possible. Secondly, we focused on parallelizing the existing code. To achieve the best compute time possible, we took a look at MATLAB's parallel computing toolbox for methods to parallelize not only the MATLAB code, but the Simulink model, so that multiple cases can be simulated on multiple cores simultaneously. And then finally, we examined optimization through MATLAB's optimization toolbox and considered how these techniques could be applied to our code once it was running fast enough to make this feasible. This block diagram illustrates our idea for how to implement these changes to the code. Inside this blue oval, you can see the original code, which consists of a MATLAB script feeding inputs to a Simulink model, which produces individual margin values, which are combined to create the overall margin score for each case. It's this section of code that we saw potential to parallelize using MATLAB's parallel computing toolbox. Here you can also see how we imagine optimization could be implemented on the code, with a threshold optimizer reading continuous margin data, using that margin data to adjust parameters accordingly, feeding these optimized and adjusted threshold values back into the Simulink model, and then rerunning the model for the same set of cases, and repeating this process until optimized margin outputs are achieved.
Within our design solution, we built a high-core lab computer to utilize MATLAB's parallel toolbox, discussed later. This testing computer is comprised of a 16-core processor, a 2 terabyte SSD to quickly read test data and write to new text files, 64 gigs of RAM to allocate block memory for each worker, and an RTX 3060 GPU. After building the machine, we wanted an accurate base computation time to compare to our parallel code. This code is shown running on 30 cases in this short clip. As you can see, the current GE algorithm utilizes a single core of computing power, which causes slow run times. To solve this issue, MATLAB designed an app to solve computationally and data-intensive problems using multi-core processors. Within this toolbox is the par4 function. It is a for-loop function that assigns a copy of the function body to individual cores for a simultaneous execution. Our second design solution was the input data. After using the MATLAB profiler, we identified the slowest section of the code, which was reading and parsing the case data. As you can see, it took 50% of the computation time to read in the case files. To solve this, we process each CSV file to MATLAB variables and save them into a .mat file for each case before running the function. Loading the .mat reduced compute times by 50%. For our parallelization results, we ran a test set of 20,000 cases. The original GE NOFD driver took 8.14 hours to run the 20,000 cases. The simple CSV to MAC conversion reduced the time to nearly 3 hours, and the parallel code took 14.9 minutes. In comparison to our time improvements, in cases per second, the original was 0.9 cases. The CSV doubled that to 1.8. And finally, the parallel code ran 22 cases per second. Here is an example simulation of the parallel code with 600 cases that took nearly the same time as the original driver code. When dealing with optimization, there are two approaches, empirical and computation. Empirical optimization analyzes the current margin values and identifies potential parameters for improvement. This is done by manually adjusting algorithm parameters and testing on a large set of cases. You then analyze the resulting margin values and adjust parameters accordingly. You then rinse and repeat. Computation, MATLAB optimization toolbox is important. This provides functions for finding parameters that minimize or maximize objectives while satisfying constraints. The objective function returns the margin value, and for inputs, it takes in variables, which are the algorithm parameters, and constraints, which are the threshold range for a given parameter. Some bottlenecks with parallelization were variable transparency. Parallel code must be transparent, meaning all workers must be able to execute their code entirely independent of each other. The second bottleneck was the simulate model workspace. It originally referenced the user workstation for values, which the workers do not see. For future directions, we advise you to implement optimization algorithm. The current optimization efforts are empirical, requiring a user to adjust parameters and review resulting margins manually. Future efforts should utilize MATLAB optimization tools to run optimization computationally. In conclusion, with the simulation parallelized, compute times are reduced low enough for computation optimization to be feasible. I want to give a special thanks to Dr. Raza and Dr. Groff with the ECU department, and a special thanks to the industry sponsor, Dr. Timothy Healy and GE, for giving us the opportunity.